Okay, salam alaikum jami'an. We carry on with our lectures. This is uh, Analytical Chemistry Part 2. We finished Part 1 and now we're carrying on with Part 2. In this part, we will talk about how to find out percentage composition and empirical formula and molecular formula. We need these, especially as you are a pharmacist, you need to know something about how to calculate and how to know the molecular formula, what does it mean, and how to find it out. The learning objects for this lecture is to understand the difference between empirical formulas and molecular formula. We have two types of formula. One is called empirical formula and the other one is called molecular formula. And the other objective is to determine molecular formula from percent composition and molar mass. As far as I remember, we explained what we mean by molar mass and how to find out the molar mass for a molecule of a compound, percentage, composition, and empirical formula. So the first thing we're going to do is talking something about determining percent composition from formula masses. I think this one is not difficult for you, and you had some idea about it before, but we're going to do it now again. So, percent composition is also useful for evaluating the relative abundance of a given element in different compounds of known formula. What does it mean? It means if we want to know abundance يعني انتشار. How much, for example, was the abundance of sodium in the, you know, on the earth, for example, or abundance of, for example, any element. So we can find out the percentage is a good idea or good tool or good technique to find out the abundance is the percentage. Let's take one example. As one example, consider the common nitrogen containing fertilizer ammonia. You know, ammonia NH3, it contains nitrogen, contains hydrogen. And this can be used to produce fertilizers, asmida, but turbo. And of course, these fertilizers are, for example, ammonium nitrate, for example, NH4NO3, or urea, which is CH4N2O. The element nitrogen is the active ingredient. طبعا we're talking about the nitrogen element in this compound to supply the soil, يعني نزود التربة for the plants. يعني النباتات تحتاج إلى عنصر النيتروجين الضروري وممكن إعطاء هذا النيتروجين إلى التربة وبالتالي إلى النبات عن طريق الأسمدة, which is called in English fertilizers. For example, we have NH4NO3. If you look at the formula of NH4NO3, there is nitrogen in it. And if you look at the urea, which is CH4N2O, and again, we have nitrogen. We use these compounds as fertilizers to supply the soil, as we said, in nitrogen. So the element nitrogen is the active ingredient. Ingredient يعني هي المادة الأساسية هنا. المادة يعني اللي يحتاجها التربة أو يحتاجها النبات for agricultural purposes, agricultural زراعية. So the mass percentage of nitrogen in the compound is a practical and economic concern for consumers choosing among these fertilizers. يعني in other words, we have different fertilizers, we have different compounds containing different percentage of nitrogen. So economically, which one giving highest percentage, that's the one which will be, that's the one we consider to use. So if you consider, for example, an H4NO3 and you calculate the percentage of nitrogen, you see it will be different than the percentage of nitrogen in urea. So which one is giving more nitrogen? That's what we want to know. So we calculate that percentage. So this is our point now. A molecule, for example, of an H3 contains one nitrogen atom, and the molar mass for that nitrogen, as you know, it's 14.01 AMU, atomic mass unit. We call it atomic mass unit, and 3 hydrogen atoms. So we have 1 nitrogen in ammonia, and we have 3 hydrogens in the same ammonia. Now, we try to calculate the percentage of each one, the percentage of each one. The formula mass of ammonia is therefore, of course, it's 14.01 plus 3, yeah, and 3 times 1,008, that's for hydrogen. So altogether we have 17.03, that's for ammonia. It's coming from 3 hydrogens and 1 nitrogen. Now, if we calculate the percentage of each one, look at the nitrogen, what we do usually for percentage, that's in general, we divide, for example, in this example, 14.01 for the nitrogen, because we have only 1 nitrogen in ammonia, and divided by 17.03 for NH3, and of course multiplied by 100 to convert it to percentage, so we get 82.27% of nitrogen. And hydrogen, similar way, is 3.02 for hydrogen, because 3 times 1,008, if you remember, we just said it now, and of course divided by the molecular formula of ammonia, which is again, it is 17.03, and again multiplied by 100 to get 17.76. So we have nitrogen percentage in ammonia is 82.27, and for hydrogen is 17.76. Remember, we're talking about mass in this case. We're not talking about the number. Not the number ratio, 3 hydrogen to 1 nitrogen. No, we're talking about mass, how much. Let's take another example. Example number 1 says aspirin is a compound with the molecular formula C9H8O4. What is its percent composition? When I say what is its percent composition, it means you have to calculate carbon, and you have to calculate hydrogen, and you have to calculate oxygen as well. Again, it's easy, similar as we did with ammonia just now, but in this case we have 3 elements instead of 2. You have 9 carbons, and you have 8 hydrogens, and you have 4 oxygens. That's the way we do it. The carbon percent, you have 9 carbons, so multiply 9 by the molar mass of carbon, and multiplied by the molar mass of the aspirin, which is C9H18O4, and again multiplied by 100 to make it percentage. So 9 times 12.01, that's for carbon, divided by 180.159, multiplied by 100, so we get 60% carbon. So an aspirin is 60% carbon. And similar way for hydrogen, in this case we have 8. So that should be H, sorry, that should be H, and that should be O. It doesn't matter, it doesn't matter. 8 more, yeah. So the percentage of carbon is 60%, and the percentage of hydrogen is 4.48%, and for oxygen is about 35.2%. So if you add them up, 60 add 4.48, add 35.2, you should get 100%. Because that's the only elements you have. We have only 3 elements in this aspirin, which is carbon and hydrogen and oxygen. So the percentage must be equal at the end to 100%. So knowing the formula of a substance, as you see, we know the formula. We know the formula for, you must know the formula so you can calculate the percentage. If you don't know the formula, you cannot percentage. Sorry. So then the percentage composition may be found by calculating the proportion of mass by mass of each element and converting it to percent. For example, again, the molar mass of carbon dioxide is 12 because you have one carbon plus 2 times 16 because you have two oxygens. So the molar mass for carbon dioxide, which is CO2, is 44.01 gram per mole. So if we calculate the oxygen, for example, oxygen constituents 32 gram per mole of this. Why is it 32? Because you have two oxygens, so 2 times 16, we get 32. So 32 divided by 44.01, we get 72.71%. Similar to the one we did with ammonia and with aspirin. I think percentage is not hard. And you see, you have about 3 examples. So what you need for percentage, you need the molecular formula, you need the molar mass for that molecular formula, and you need to just divide the molar mass for each element, of course, multiplied by how many atoms. For example, with ammonia, we said 3 times hydrogen. And in this example, we said 2 times oxygen because you have 2 oxygens. So you should consider that number as well. Move to the empirical formula. So what we mean by empirical formula? So we're giving you some definitions might help you to understand what we mean by empirical formula. Empirical formula, a formula giving the proportions of the elements. What we mean by proportions of the elements, it means like how many atoms for each one. For example, how many carbon with how many hydrogen with how many oxygen present in a compound, but not the actual numbers. Remember, empirical formula is not giving you actual numbers. It's giving you just the ratio between these elements or arrangements of atoms. Means it doesn't give you the structure. Or we can say the empirical formula of a compound is the simplest whole number. Simplest, look at the word simplest. With some examples, you might understand it better way. So it's the simplest whole number ratio of atoms of each element in the compound. It's determined using data from experiments. Yeah, let's concentrate on this point a bit. Is calculated from experiments and therefore empirical. So the empirical means these data is was obtained by experiments. It's not something theoretical. For example, the molecular formula of glucose is C6H12O6. So that's the actual formula for glucose. In each molecule of glucose, we have 6 carbons and 12 hydrogens and 6 oxygens. But the empirical formula is CH2O because the ratio between 6 and 12 and 6 is 1 to 2 to 1. So that's why the empirical formula is CH2O. So this formula, I mean the empirical formula for glucose, is not the actual formula. This is the actual formula, but this is just giving you the ratio between the atoms. So this is empirical formula. Sometimes there is another name for empirical formula, which is not very common. We call it simplest formula of a compound. And this empirical formula indicates the elements present in the compound. So the empirical formula telling you what elements in the compound. You go back again to the example of glucose, telling you in the glucose there is carbon, and there is hydrogen, and there is oxygen, and there is nothing else. You have three elements in this glucose. So that's point one. The elements present in the compound is telling you, the empirical formula telling you that. And it's telling you the simplest tool, as you see in this example, number ratio of these elements. So it is 1 to 2 to 1. It doesn't mean the glucose molecule is only one carbon or two hydrogen or one oxygen. No, it's just giving you the ratio between them. And as I said before, the actual formula is C6H12O6. So in general, how can we find out the empirical formula? It may be found by dividing the coefficients in the molecular formula by their highest common factor. For example, the molecular formula of glucose, as we said, is 6C6H12O6. So its empirical formula is CH2. I think this is repeated again. We explain this point. So if the mass of the elements in a compound is found by experiment, empirical means by experiment, if we found out the mass for each element in that compound by an experiment, how much, for example, carbon in this compound, how much hydrogen in this compound, how much oxygen in this compound. So the first thing you need to find out the mass for each element, and that can only be done experimentally. So then the amount of each element may be found using its smaller mass. If you remember, the number of moles is equal to the mass of that element divided by the molar mass of the same element. Let's go to this example. If we have very simple example, we have 2.476 gram of an oxide of copper. We don't know the oxide, just we know it's an oxide for copper, found to contain 2.199 gram of copper. So we know the mass of the copper, and we know the mass of the oxide. Determine its empirical formula. Now, if we look at the equation, it says oxide of copper. It means we have only oxygen and copper. So if you know the mass of the copper, I think simply you can find out the mass of the oxygen. You have 2.476 of the oxide, and you have 2.199 of copper. So the difference in weight is for oxygen, obvious. So the oxide therefore contains about 0.277 gram of oxygen. Now we know the mass for the oxygen, and we know the mass of the copper of the compound. So that's the first step. We need to know the mass, or sometimes we give you the percentage. We give you the percentage for each one, and you can use the percentage as a mass. I will show you that later. So the amount of each element can therefore be calculated using the molar mass. For oxygen, it's 16, and for copper, it's 63.55. Now, what are we saying? We're saying amount of oxygen. In general, when we say amount of oxygen in chemistry, we mean how many mole. We mean how many mole. We don't mean the mass. We mean how many mole. So the amount of oxygen, we're taking the mass, which is 0.277 gram, divided by the molar mass of the oxygen, which is 16.00 gram per mole. So we get 0.01731 mole. That's how many moles of oxygen in the compound. And in a similar way for copper, you're taking the mass, which is 2.199 gram in this question, divided by 63.55 gram per mole. That's the molar mass for copper. And we get 0.03460 mole. That's the number of mole of copper. So by now, we know how many mole of oxygen and how many mole of copper in this oxide. Now, the whole number ratio of oxygen to copper may be found by dividing through by small number. So ratio of oxygen to copper is number of mole of oxygen to the number of mole of copper. We get something about 1 to 1.999. And you might ask how we get this. How we get this? You have this number, that's the number of mole of oxygen, and this is the number of mole of copper. That's the ratio. What we need to do, remember this always, divide both this number and this number by the smallest one. Which one is the smallest one? Is this one, of course. So divide this by the same number, because it's the smallest one, and divide this number by this number. So you get something. So this would be, of course, 1, and this one is something about very close to 2. So it looks like we have 1 oxygen for oxygen to copper, or 2. So it's something like Cu2O, Cu2O. We have copper 2 and oxygen 1. Of course, sometimes we don't give exactly whole number as integer number, but we will deal with this and how to find it out or how to sort it out. So in some cases, this does not give a whole number, and then multiplying by a small integer will be necessary. For example, ratio of Fe to oxygen of 1 to 1 and third, 1 and 1/3. Right, so what shall we do in this case? We can multiply the 1 by 3 and the 1 and 1/3 by 3 as well. So if you multiply this by 3 and this by 3, you get an integer numbers. Right, just 1 minute. Let's say Fe, something times 3, and O times 3 again. So for Fe, we get 1. We get 1 times 3. So like 3 Fe. And for oxygen, again, 1 and 1/3. Times 3. something like 4. So it is Fe3O4. Okay, right. And we don't need this. Right, we have another example, says determine the empirical formula of a compound of phosphorus and oxygen. So we have phosphorus and oxygen. Compound contains only phosphorus and oxygen that contains 3.64% phosphorus by mass. Of course, remember we're talking about mass, not how many. You're not taking the percentage of how many as a number. You're taking it as a mass and then as a mole. So in this example, you know the phosphorus was the percentage. Obviously, you can find out the oxygen because you have only 2 elements, phosphorus and oxygen. So if you know the phosphorus, obviously you can find out the oxygen. What we do in this case, in general, we consider we have like 100 gram of the compound. Consider you have 100 gram. So there are 3.64 gram of phosphorus. When you take 100 gram of the compound, and the percentage of phosphorus is 3.64, it means for the 100 gram of the compound, you have 43.64 gram of phosphorus. And of course, you have about 56.36 gram of oxygen. I think you know how we did this. You just take away 43.64 from the 100, you get for the oxygen, which is 56.36. So what's the amount of phosphorus then? I mean, how many moles of phosphorus? You simply divide that mass by the molar mass of phosphorus. And for oxygen, you divide and you divide again the mass of the oxygen by the molar mass of the oxygen, and you get this mole, which is 3.523. So by now you have the number of moles of oxygen and the number of moles of phosphorus in this compound. This is a phosphorus oxide. So the whole number ratio of phosphorus to oxygen may be found by dividing through by the smaller number. If you remember what we said, you take the ratio like 1.409 to 3.523. So why we do that? Why we divide it by smallest number? This is the ratio, of course. It is 1.409 to 3.523. That's the ratio between phosphorus and oxygen, which is not wrong. But what we do, we convert these decimals number to an integer number because the formula must be written in integer number, not in decimals. يعني يجب أن نكتب عدد صحيح وليس كسور. So if we divided 1.409 by 1.409, which is the smallest one, so we get 1, of course, And if you divide this 3.523 by this small number, you get something like 2.5. Of course, we don't keep it 2.5 because, again, 2.5 is not integer number. So what we do, if we multiply both of them by 2 to keep the same ratio, so this would be 2 and this one would be 5. So 2 to 5 is same as 1 to 2.5 and is same as to 1.409 to 3.523. All same ratio. We're not changing the ratio. We're keeping the ratio. The only thing we're doing is to converting the decimals number to integer numbers. In this case, it is necessary to multiply by a small integer, in this case 2, in order to produce a whole number ratio. The empirical formula then it is P2 because P is 2, O5. It is P2O5. Of course, similar technique may also be applied to calculate the amount of water of crystallization in hydrated salts by calculating the ratio of the amount of water to the amount of anhydrous salt. Right. I think in summary, we can say calculate the amount in moles of each element or component as the first step. You convert, remember, the mass to number of mole. That's the first step. If you don't have the mass directly, you have a percentage. You consider that percentage as a mass. Consider you having 100 gram of the sample and you take the percentage as a mass. Deal with it as a mass and divide it by molar mass, you get the number of moles. And then find the simplest whole number ratio between these amounts. Simplest whole number. It means integer number, not decimal. Right. So empirical formula can often be found by direct determination. For example, converting a weight sample of one element to the compound and then weighing the compound to find the mass of the second element that's combined with the others. For example, you have Cu with oxygen to make CuO. If you know one of them, you can find out the other one. If you know the one of them, you can find the other one. Another method, another method is to decompose a weight sample of a compound containing only two elements. For example, you have Fe2O3, decompose it to Fe and O2. So of a compound containing only two elements so that only one element remains and then finding the mass of the element. So this second method is similar to the one that's usually used to determine the formula of hydrated salts. That's what I mean by hydrated salts. If we have CuSO4, 5H2O, that's none, of course, because copper sulfate takes 5 water molecules. We call this hydrated salt. Hydrated salt. The water molecules is combined with the salt. By heating, we giving heat to this compound, that copper sulfate, which is a blue color, starting to losing the water molecules, of course, step by step, until that water separated from the CuSO4, we get CuSO4 without water. We call this anhydrated copper sulfate, and we call this one hydrated copper sulfate. This is another technique. You can find out how many water molecules is given. Okay, the percentage composition of organic compounds, let's talk about organic compounds, usually found by burning. So we use burning, yes, burning. That's we're talking about organic compounds. Talking about organic compounds. Burning a non-mass, we know the mass, a non-mass of the compound in excess oxygen. Why are we saying excess oxygen? We're saying excess to make sure that all the compounds burned and all the elements, excuse me, and all the elements converted to oxides. Then finding the masses of both carbon dioxide, all carbon is converted to carbon dioxide and water converted to water. Look at the equation. I think that's what's explained to you what we're saying. We have, this is an example of an organic compound. This is an example of an organic compound. We burned that organic compound in oxygen. And remember, all organic compounds contains carbon and hydrogen. Some contains oxygen or any other elements as well, and some without any other elements rather than carbon and hydrogen. In this case, we call it hydrocarbons. So all hydrocarbons are organic compounds, but not all organic compounds are hydrocarbons. This is a hydrocarbon, which is again organic compound. When it burns, reacts with oxygen, it gives carbon dioxide. All the carbon change to carbon dioxide and all the hydrogen change to water. So of course, oxygen must be enough, must be sufficient oxygen to make sure that all carbon is now CO2 and all the hydrogen is H2O. Because if the oxygen is not enough, not excess oxygen, we don't get all our CO2. We might get CO instead, carbon monoxide, or even sometimes we get just carbon without oxygen, which we call it soot. So that's why we said excess oxygen. So the mass of oxygen when the organic compound contains oxygen can be found by subtracting the mass of these two elements from the initial mass, assuming that this is the only other element present. This is another example, 2.8 gram of an organic compound containing only carbon and hydrogen forms 8.80 gram of carbon dioxide. So we know how much carbon dioxide we have, and 3.6 gram of water. So we know how much water we have. That's what we need. And we have the sample, the mass for the sample. So it says determined its empirical formula. Now, because carbon dioxide contains only one carbon, so all the carbon converted to carbon dioxide, it has the same number of moles. So the amount of CO2 which is given out is the same as the amount of C. So what's the amount of C then? It's the mass, what mass we're having, divided by the molar mass. So we have something like so you might ask a question. You say, okay, this is 8.8 gram is the mass for carbon dioxide. Okay, that's true. And how come we use this mass for the carbon? That's not the mass for carbon. That's the mass for CO2. Yes, this is the mass for CO2, and this is the molar mass for CO2 as well. So this is the number of mole of CO2, which is the same number of moles of carbon as a number of moles, carbon dioxide and carbon same, because each CO2 having only one carbon. Now, what about amount of H2O is the equal amount of H? That should be 2 So what's the amount? Okay, how many more? Yeah, that's here. Yeah, okay. But remember, for CO2, you have one carbon for each one CO2. So the number of moles of CO2 same as the number of carbon. But for hydrogen, the number of moles of water is not same as the number of moles of hydrogen because each water molecule contains two hydrogens. So in this case, if you have one mole water, it means you have 2 moles hydrogen. So that's why we multiplied in this case by 2. Okay, that's the amount of water. Again, you take the mass of water, you divide it by the molar mass, and you get the number of moles of water, which is this one. But this number of mole in this case is not similar as with carbon dioxide and carbon. In this case, is different. In this case, you have 2 hydrogens for each water. And that's why you have to multiply it by 2. So we have something about zero point 0.4 mole of hydrogen. So this is number of mole of hydrogen, and this is the number of mole of carbon. So I think it's very easy. This one is zero point 0.4. This is zero point 0.2. So carbon to hydrogen is something like 1 to 2. 1 carbon for each 2 hydrogen. 1 carbon for each 2 hydrogen. So simply the empirical formula is CH2, 1 carbon. Let's take this example. Consider vitamin C, a compound that contains carbon, hydrogen, and oxygen only. Uh, why we said only, just to make sure for the students, there is no any other elements. You have only 3 elements. On combustion, يعني بالاحتراق, of 1 gram vitamin C, we burned 1 gram vitamin C, 1.5 gram CO2, and 0.408 gram H2O are produced. This example is similar to example 4. You can do it the same way. You have CO2, so you can find out the number of moles of carbon because you have the mass and you have the molar mass for CO2. You divide 1.5 by molar mass of CO2, the amount of CO2, which is the same as the amount of carbon. So you have the number of carbon mole. And similarly with water, as we did in example 4, you divide 0.408 by molar mass of water, you get a number of moles of water, and then multiply it by 2, because each water molecule giving 2 hydrogens. So you should multiply the number of moles of water by 2 to get the number of moles of hydrogen. And the oxygen, of course, will be the rest of the 1 gram. You have 1 gram. Okay. So the rest should be, of course, for oxygen. We found that the mass, let me make sure you understand this example. So all the carbon and CO2 came from vitamin C. The mass of carbon is 1.50 gram. CO2 can be easily calculated. So if you know the mass of CO2, Where is it? Yeah, 1.5. Now find out the mass of carbon, how much carbon in it. And I think similarly with hydrogen, that's the masses for carbon and hydrogen and oxygen. And you know the molar mass or the atomic molar mass for carbon is 12, something about 12, for hydrogen is 1, for oxygen 16. So you divide the mass by this atomic molar mass, you get how many mole for each one. So we know the number of mole carbon and we know the number of mole hydrogen and for oxygen. Once you know the number of moles, and that's it. You found out the ratio. But as we said before, you cannot write the ratio like these decimal numbers. We should convert it to integer numbers. So if we take the smallest number, which one is the smallest one? I think this as same as this. So this is the smallest number. So you divide this by itself, and you divide this one by this number, and you divide this again by this number, you get something 1, 1 and a third, and 1. Multiply all of them by 3 to get this 3 and this 1 and 1/3, going to be 4, and this one is going to be 3. So it is 3, 4, 3. Therefore, the empirical formula of C is C3H4O3. This example, we're giving you the percentage of each one. Again, as we said before, you consider this percentage as a mass for each one, for each element. This one, carbon, hydrogen, nitrogen. Remember, this is not oxygen, nitrogen. You can find out the mass for each one. Convert the percentage as a mass. So that's the percentage. Sorry, this question is not telling you there is an oxygen as well. Okay. Yeah, you have 40 and 4, something if you consider this as 40 and 4, and not 100%. The total is not 100%. And there is oxygen. Okay, sorry, it's not mentioned in the question clearly. So you have 4 elements in this question. You have carbon, hydrogen, nitrogen, oxygen. You know the percentage for these. You can find out for this one. Add them up, these 3, add them up, and take it off from 100, you get 4. And you know the AR, which is the atomic molar mass for carbon and hydrogen and nitrogen. You divide this number by this number, you get the ratio 1.9, 4.8. Now divided by simplest one. So the simplest one, I believe it's something like this one or this one. Well, it's not that different. Let's say this one, something like 1, 2.5, 1.5. Again, you don't have integer number, you multiply all of them by 2 to make this 2, and this one make it 5, and this one 3, and this one 2. So empirical formula is C2H5N3O2. Right, you have some exercise, you need to work it out, and we stop here for molecular formula. do it next session. Thank you very much. If you have any question, as we said before, ask, you can contact, and I will be more than happy to reply to your question or to your request. Thank you very much, and see you again in the next